All right, so today we're talking about the law of conservation of mass. And the law of conservation of mass was first sort of discovered by a French scientist named Antoine Lavoisier. And he was a French aristocrat living during the French Revolution. And he had a lot of money and he did a lot of very exact calculations. And he basically observed that even though there was chemical changes occurring, the total mass involved in the reaction stayed constant. So he was the first one to actually come up with the law of conservation of mass, which basically states that matter can't be created nor destroyed, or mass can't be created nor destroyed during a chemical reaction. It's conserved. It can just be rearranged. In other words, your mass of your reactants has to equal your mass of your products. Alright, so before you watch this video, you need to be thinking about how to answer these questions. Where did the mass of the missing water go in Lavoisier's first experiment? What did he do in his second experiment? And did his experiment support the law of conservation of mass? So make sure you answer those three questions as you watch the video.
This way, please, gentlemen. Monsieur, it is my great ambition to demonstrate that nature is a closed system, that in any transformation, no amount of matter, no mass, is ever lost and none is gained. Over here, please. This precise amount of water is heated to steam. This steam is brought into contact with a red-hot iron barrel embedded in the coals. From this end, we cool the steam. But interestingly, we collect less water than we started with. So clearly, we lose a certain amount of water. However, we also collect a gas, and the weight of the iron barrel increases. Now, when we combine these two increases, the new weight of the iron barrel and the gas we have collected, they are exactly equal to the weight of the lost water.
Ah, but is it atmospheric air, Monsieur Lavoisier?
No. No, because I am measuring it to the very last grain. I can see that it is lighter than the air around us, and moreover, it is flammable. Voila.
Water is made out of hydrogen and oxygen. So what he had done is get the oxygen to stick to the inside of a red-hot iron rifle barrel. He was basically just making rust, which is oxygen and iron, but he was making the rust really quickly. Now that left the hydrogen, what he called combustible air, and that was just floating around as a gas. No mass had been lost, it had merely been transformed. And now he wanted to transform it all back into water.
This is only the beginning. In the next few months, I hope to demonstrate that I can recombine this combustible air with vital air and transform them both back into water. I will recreate exactly the same amount of water that was lost here in this process. It is my hope to complete the cycle, water into gas, into water, and not a drop lost.
For a long time, Lavoisier had suspected that the exact amount of matter, the mass, involved in any transformation was always conserved. But to prove this, he had to perform thousands of experiments, and he had to do the measurements with incredible accuracy. That's where his great wealth from being a tax collector came in. He could afford to commission the most sensitive instruments ever built. He became obsessed with accuracy.
expose this persecutor of yours.
For years, the Lavoisiers burned, chopped, melted, and boiled every conceivable substance. They'd shown that as long as one is scrupulous about collecting all the vapors, liquids, and powders created in a transformation, then mass is not decreased. Liquids might become gases, metals may rust, wood may become ash and smoke, but matter, the tiny atoms that make up all substances, none of it is ever lost. The crowning glory of this opus was their remarkable use of static electricity to cause oxygen and hydrogen to recombine back into water.
Alright, now there's going to be a second video that I want you to watch over an animation concerning conservation of mass. And you need to fill in these blanks in these questions, answer the questions as it goes through. Matter is neither blank nor blank, it is only blank. What two elements were the reactants in the little animation that they show you? What was the product? And then fill in the numbers here. Blank zinc atoms reacted with blank sulfur atoms to form blank zinc sulfide molecules. And then I want you to write the equation for the reaction.
The law of conservation of mass states that in a chemical change, matter is neither created nor destroyed. It is only rearranged. For example, let's place 5 zinc and 5 sulfur atoms onto the two sides of a pan balance. The two sides balance because the contents of each pan are identical. Consider the reaction of zinc with sulfur atoms on one side of the balance to form zinc sulfide. 5 zinc atoms will react with 5 sulfur atoms with a tremendous release of energy to form 5 zinc sulfide molecules. The two sides still exactly balance. The total number of zinc and sulfur atoms on each side are still identical, demonstrating the law of conservation of mass.
And this video demonstrates with actual materials in a lab the law of conservation of mass. And I want you to think about answering these questions. What was the mass of the reactants, meaning the starting mass? What was the indication of a chemical reaction in this experiment? What was the mass of the products, or the final mass? And then write the balanced chemical equation for the reaction that occurs in this video. Okay, so finally, how do we solve these conservation of mass problems? Well, you need to remember that the mass of the reactants are equal to the mass of the products. It's the most important thing to remember in this, so that your total mass on your reactant side is equal to the total mass on the product side. You need to be using the guess method for this, and you have to read the problems very carefully so that you know what your reactants and what your products are. And then you're going to write your givens down, including the masses, substitute your numbers into the equation, and solve for either the reactant mass or the product mass. And I've got two examples here. In example number 1, we've got an experiment where 10 grams of red mercury 2 oxide powder is placed in an open flask, and it's heated until it's converted to liquid mercury and oxygen gas. The liquid mercury has a mass of 9.26 grams. What is the mass of the oxygen formed in the reaction? Alright, so you know two masses. You just got to figure out where they belong. So you need to understand this word right here. Converted is sort of your key word that tells you where the reaction is taking place. So the red mercury 2 oxide is before that word converted, so that means that this is our reactant and it's converted into mercury and oxygen gas. So in this case we have one reactant, mercury 2 oxide, and we have two products, liquid mercury and oxygen gas. So as far as our givens, we've got our two masses, and then we've got this equation taking place here where our reactant, mercury 2 oxide, is yielding liquid mercury and oxygen gas. So it asks us in the question for the mass of the oxygen formed. That's another key, that oxygen is a product. So we know we're looking for the mass of oxygen, and now all we have to do is think about that equation of mass of reactants equals mass of products and put our numbers in the right place. So we know that the 10 grams of mercury 2 oxide is a reactant, and we know that the 9.26 grams of liquid mercury is one of our products, and that we're looking for this oxygen mass. So we just stick those into the equation, that 10 grams is equal to 9.26 grams plus the mass of oxygen. And then we just solve the equation. So if we're solving for mass of oxygen, that means that we need to subtract 9.26 grams from both sides. So when we subtract 9.26 from 10 grams, we're left with 0.74 grams, which is the mass of the oxygen. Remember again that the total mass of your products has to equal the mass of your reactant. So that's kind of your check. 9.26 plus 0.74 equals 10. So we know that we did this correctly because those two sides have to equal each other. You can't do these problems though if you don't know what your reactants are versus what your products are. So you really have to make sure that you can read these problems correctly to be able to do this. Alright, second example. When 33 grams of wood was burned in air, it combined with 32 grams of oxygen to form 3 grams of ash and a gas mixture of carbon dioxide and water. When the gas mixture was cooled, 18 grams of water condensed. How much carbon dioxide was formed? Alright, so 33 grams of wood was burned in the air, and it was combined with 32 grams to form. Alright, so we've got wood burning in air in the presence of oxygen. So we've got wood and oxygen. These two things are our reactants, and they're forming. So here's our arrow, our yield sign. We're forming 3 grams of ash and also a gas mixture of carbon dioxide and water. Okay, and it tells us the mass of the water that was left over. So we've got the mass of 2 reactants, and we also have the mass of our product here, okay, along with our other product, and then we don't know how much carbon dioxide was formed. So we do know that we start with wood and oxygen, and we end with ash, water, and carbon dioxide. We know that we're given the mass of the wood and the oxygen, the ash, and the water. We do not know this carbon dioxide, so that's our unknown. Again, the total mass of our reactants has to equal the total mass of the products altogether. So all of this on this side has to equal all of this on this side. That's what those plus signs mean. And you can think of our arrow, our yield sign, as also being like the equal sign in the reaction. Okay. So then we just substitute in our numbers. We know that we have 33 grams of wood and 32 grams of oxygen, and that has to be equal to the mass of our ash, 3 grams, the mass of the water, 18 grams, plus the mass of carbon dioxide. So the first thing you need to do is simplify this by adding 33 and 32, and that gives you 65. And then you also need to add your 3 grams and your 18 grams, and that gives you 21 grams. And you've got your mass of your carbon dioxide. At this point, it becomes just like the first example. We've got 21 grams plus the mass of carbon dioxide is equal to our 65 grams of our reactants. And so we need to subtract 21 grams from both sides to get the mass of the carbon dioxide. So when we subtract 65 from 21, we get the mass of carbon dioxide, which is 44 grams. Again, our check can be by looking back at this and adding it up with the rest of our products. So 44 plus 21, or 44 plus 3 plus 18, also equals 65 grams. So we know that we did this correctly. Remember, the key to this is that the total mass of your reactants, everything you've got on the left side of your equation, over here on the left side of your equation, has to equal everything on the right side of the equation. It has to be the total mass of your products. So all of this together has to equal everything on the left side. And that's how you do these equations. And it doesn't matter if you've got 2 things or you've got 10 things on either side. The principle still is the same. Total mass of reactants equals total mass of products. And you've got to put your numbers in the right place by reading the problem carefully, and then it's very easy math. All you're doing is adding and subtracting. So I hope that you get the idea of how to do law of conservation of mass with mass numbers for your reactants and your products.